In March 2021, during a promotional event, a payment integration team began receiving 429 errors from their payment gateway API. They had never seen a 429 in production before. They assumed the gateway was experiencing an outage. A reasonable inference, since an error is an error. They contacted support, drafted an incident communication to customers, and spent 45 minutes investigating infrastructure that was running without fault. The gateway was operating normally. The 429 came with a Retry-After header that specified, in seconds, exactly how long to wait before sending the next request. The service was not failing, it was communicating. The fix was reading a header that had been present in every error response for 45 minutes. The assumption embedded in almost every alert system and incident response protocol is that an error means something has gone wrong. An error rate that climbs from 0 to 5% is an anomaly. An anomaly means failure. Failure means investigation. This assumption serves well most of the time. It does not serve well when the errors are coming from a limit enforcement system, because limit enforcement errors are not failure signals. They are instructions. When a cloud service enforces a limit, it returns an error. The error looks, from the outside, like every other error. A non-200 HTTP response code, a message in the response body, an entry in the application logs. The alert fires. The on-call engineer wakes up. The investigation begins. But the enforcement error is not telling you that something has broken. It is telling you what the service is doing in response to your request pattern, and, in the well-designed ones, what it expects you to do next. The further complication is that the same application, with the same code, can receive different enforcement behaviors from different services in its dependency chain simultaneously. One upstream service might be throttling, while another is rejecting entirely. The error signals arrive in the application logs as a mixture of codes that require individual diagnosis. An incident response protocol that treats all errors as equivalent will apply the same response to all of them, which will resolve some and worsen others. Reading the enforcement error correctly is what determines whether the next 45 minutes are spent on the wrong investigation or on the right fix. Think about what happens when you encounter an obstruction while driving. If you reach a red traffic light, you stop. You do not turn around. You do not call the road authority to report an infrastructure failure. You wait because the red light tells you something specific. This path is temporarily unavailable and it will reopen. The correct response is to wait and then proceed. If you reach a road closure sign, the situation is different. The sign tells you the path ahead is not temporarily unavailable, it is blocked, and no amount of waiting will change that. The correct response is to find a different route. Sitting at a road closure and waiting for it to lift is the wrong response, not because waiting is wrong in general, but because the signal in front of you is telling you something different from what a red light tells you. Both a red light and a road closure sign stop your forward progress. Both produce the same immediate experience. You cannot continue this way right now. But the appropriate response to each is completely different, and confusing them has consequences. A driver who treats a road closure as a red light will wait indefinitely. A driver who treats a red light as a road closure will add unnecessary time to their journey and may miss the moment the light turns green. Cloud limit enforcement errors work on the same logic. Some say wait and retry, the path will reopen. Others say this route will not open regardless of how long you wait, and you need to find a different approach. The error code and the response structure are the signs at the obstruction. Reading them determines what comes next. The analogy has a limit worth naming. Road signs are designed for unambiguous interpretation. A red light means the same thing everywhere. Cloud error codes are not standardized across providers or even across services within the same provider. The same HTTP status code can mean different things depending on which service returned it. The analogy is cleaner than the reality. Cloud services enforce limits through 4 distinct mechanisms. Each produces different signals and requires a different response from the application receiving them. The first is throttling. The service accepts that a request arrived, but slows or delays its processing because the incoming rate has exceeded the permitted ceiling. Throttling is the enforcement behavior designed to be survived. The service returns a 429 status code, too many requests, often accompanied by a retry-after header specifying, in seconds, how long the client should wait before sending the next request. The path is not closed. The service is asking the client to reduce its rate and try again. An application that reads the retry-after header and waits accordingly will resume normal operation within seconds to minutes. An application that retries immediately on a 429, without waiting, will continue to receive 429 responses and may trigger more aggressive enforcement behavior from the service. The second mechanism is rejection. The service refuses the request with no suggestion that waiting will help. This appears as a 403 forbidden or as a 400 series error code with a specific message indicating a limit type that cannot be resolved by reducing request rate. Hard resource limits, account level ceilings that require a quota increase to change, and architectural limits that cannot be modified at all are enforced through rejection rather than throttling. Retrying a rejection at any interval will not succeed. The application needs to change its approach, request a limit increase through the provider's support process, redesign the workload, or distribute the load differently. Retrying is the red light response to a road closure. The third mechanism is queuing. The service accepts the request and returns a success response, but delays processing it, absorbing excess load into an internal buffer rather than returning an error immediately. From the application's perspective, the request succeeded. The response code is 200, no error is logged. But latency climbs, sometimes significantly, as the queue absorbs more work than it is processing. Queuing-based enforcement is the most forgiving in the short term and the most dangerous if ignored, because the visible signal is a latency increase that can be mistaken for a performance issue or a slow dependency. Queue depth metrics, where the provider exposes them, are the relevant monitoring signal, not error rates. The fourth mechanism is circuit breaking. Under sustained high load, some services stop accepting new requests entirely and return failures immediately, rather than accumulating timeouts. The circuit open state protects the service from collapse by shedding all new load, but it means requests that would have succeeded under normal conditions are now failing at the service entry point. The correct response is a significant reduction in load, followed by a waiting period for the circuit to reset, not retries at the current rate, which keep the circuit open, and not immediate escalation to infrastructure investigation, which will find the infrastructure healthy. Identifying which mechanism a service is using requires examining more than the HTTP status code. The response headers carry the fuller picture. A 429 with retry-after is a throttle with a recovery instruction. A 429 without retry-after is a throttle with no instruction. The client must implement its own back-off strategy, typically starting with a short wait and doubling it on each subsequent failure. A 403 with a specific error code referencing a limit type is a rejection pointing toward its own resolution path. A 503 requires checking the response body and the provider's service health page to distinguish enforcement from genuine infrastructure unavailability. The most significant practical complication is that error codes are not standardized across cloud services. A 503, service unavailable, is the conventional code for infrastructure failure. Some services also use 503 for rate limit enforcement, because from the service's perspective, that resource is genuinely temporarily unavailable to that client. A 429 is the conventional code for rate limiting. Not all services use 429. Some use 503. Some older APIs return 200 with an error payload embedded in the response body that must be passed to distinguish a successful call from a limit hit. Reading enforcement signals correctly therefore requires knowing not only what a status code means in the HTTP standard, but what a specific service uses it to mean. This information lives in the API documentation, in the error code reference sections, pages that are worth reading before the first line of integration code is written, rather than after the first production incident reveals the gap. A further complication is silent dropping. Some services, under back pressure conditions, accept a request, return a 200, and do not process it. The application believes the request succeeded. The audit trail later reveals it did not. This enforcement behavior appears in message queuing systems and event streaming platforms at high load, and it is the mechanism most difficult to detect through error rate monitoring alone. Confirming that a service processed what was sent through delivery confirmations, audit logs, or downstream state verification is the detection mechanism for silent dropping. The payment team's 429 was not a failure signal. It was a statement from the gateway. The permitted request rate has been exceeded, and here is precisely how long to wait before the next attempt. Reading that statement, looking at the Retry-After header, was a fix measurable in seconds. Not reading it and treating the error as infrastructure failure was a 45-minute investigation that found nothing wrong because nothing was wrong. Every enforcement error a cloud service returns is a communication. It describes what the service observed, what it did in response, and, when the design is good, what the client should do next. The signal is in the error, not in the infrastructure behind it. The investigation that starts with the error message, rather than with the infrastructure, is usually the shorter one. When a limit is hit, the service speaks first. The conversation goes better when you know how to listen.